Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from Texas Instruments. We have Arnon Friedmann. He is the multi-core business manager for the company. So, Arnon, welcome to the show today.
Yeah, hi, Rich. Thanks for having me back.
Yeah. So we're coming off of SC12. Did you have a good show this year?
Yeah, I thought it was a great show. All kinds of exciting things going on in high-performance computing, from the new powerhouse announcements from the established players to a lot of interest in what ARM's doing and our new system-on-chip devices that I'll be talking about that incorporate some of the latest ARM cores in them. So yeah, I think just across the whole show, it was really interesting, and we certainly had a lot of interest at our booth.
Well, good. I think you're coming into this market at the exact right time, because it seems like everyone's talking about power efficiency and alternative ways to achieve that, because they're running into what they're calling the power wall. So they just can't get any more electricity into the building, it seems like.
Yeah, well, it's definitely fortuitous for us. We've been running into power issues in our networking days. Most of our devices are coming from communications infrastructure, where they have trouble getting power to the base station towers, and operating expenses in terms of power consumption have been a major issue for network providers for a long time. So yeah, we've seen this, and that's a good angle for us. So yeah, it is an exciting time.
Well, good. Well, why don't we jump into it here? We're here to talk about the new KeyStone devices. I brought your slides up. Why don't we start there?
Yeah, well, we just launched our new KeyStone 2 SoCs at the show, so that was great. And in our announcement, we talked about a better way to cloud. And really what we mean is that there's a lot of processing happening back in servers or cloud computing. And as you mentioned, the challenges are certainly power consumption, but also scalability, general performance, able to do all the different things you're trying to do, and the networking, getting packets through the data. And so what we're really talking about when we say a better way to cloud is trying to enable purpose-built systems. So one way to reduce the cost and power consumption of these systems is to really target specific servers for specific jobs, instead of having just one giant server trying to do everything. So part of this is HPC applicable, and part of this is a little broader that I think should still be of interest. And then as we go further into the presentation, I'll focus more back just on the HPC aspects of what we're doing. So if you look at the second slide, a better way to cloud, really we see three aspects where our SoCs play. One is in general purpose servers, and this could be general purpose high performance computing, where we're coming in as an accelerator and trying to offload the floating point precision, and where we have a very good gigaflops per watt metric. And then in addition, with the ARM cores now, and with the ARM A15s and our infrastructure of our SoCs, we believe you can now go to real full purpose-built systems that are ARM plus DSP, ARM plus accelerator, that don't have x86. So instead of the traditional heterogeneous computing that we see out at SC12 everywhere, and I think Titan, the number one computer now, is based on that, is x86 plus accelerator, we can be completely just a sea of SoCs talking to each other. And we think that's this is a very exciting time for this, because a lot of people are starting to look outside the box of what other things can be done for HPC. So that's where most of the talk will focus. But when I talk a little bit more about our cloud computing, there's another very interesting aspect, and here it's in the second bullet, enhancing enterprise and industrial applications. And this is really focused on the data collection aspect of computing, cloud computing, high-performance computing, you name it. When you capture the data, there's just a flood of data coming into the systems, whether it's oil and gas exploration, we see in video surveillance, in video content and delivery. The networks are really just being flooded with data. So one thing that you can do to try to cope with this is to put some of the processing out at the edge. And one of the nice aspects of our SoCs is that we scale down quite small, under 5 watts. We can go out in a camera. We can go out at a data collection site. We can take some of that first-level processing out to the site and reduce the amount of traffic that has to be sent back over the network, and also reduce the amount of processing that has to go back in the server. So it really wins on two aspects, and it's really not the focus of our discussion today, but it's a very interesting aspect where, I think at SC12 we see everybody talking about scaling up to exascale. We talk about being very good at scaling out to the edge and handling some of the problems that are happening out in the real world where we're collecting the data before we compute it. So that's the second bullet. And the third bullet is upgrading our networking. And again, in cloud computing, with all the data coming through the web, coming over the internet through all different ways, there's just a lot of internet networking routing that has to happen. And so what you'll see in our SoCs is some of the SoCs that we released this week have very powerful accelerators for doing network and packet processing. And so a purpose-built system with our ARM and DSP SoCs and these network coprocessors can be very power and cost efficient for just the networking aspect of what's happening in the cloud. So those are really the three aspects of the SoCs. And then when going to the actual announcement of these 6 KeyStone systems on a chip, the one to really focus on is the 66 AK2H12, which is in the top left of that. So that's really our high-performance computing flagship product. And what that is, it's a quad ARM Cortex-A15 cores and 8 C66X DSP cores, the same DSP cores that we announced last year at the show, and that we talked about the great gigaflops per watt that they can produce. And at the show, as you saw when you stopped by, we had a lot of demonstrations of how we have now taken that DSP and started integrating it into larger HPC-type systems, where we showed the Linpack benchmark at 2.1 gigaflops per watt, which is very close to the tops of the list, as well as OpenCL running. We had OpenMP running from ARM to the DSP. So really, we're stepping up our game in terms of bringing the tools that HPC users need and use to develop applications on our SoCs. So I won't go into detail of the rest of the family here, because that's really the flagship for HPC. Certainly, if any readers or listeners are interested, please follow up with us, and I think we'll focus on that one. Just a couple more things on this page. This is 28 nanometer process technology. We do scale from 2 to 12 cores, so as I mentioned, we can go pretty low in power, so we can go out to the edge. And we're really targeting these purpose-built servers and these enterprise and industrial applications.
So if you look at the chip design, this is very similar to what we showed a year ago. Last year's device was based on a Keystone 1 architecture. This year's device is based on a Keystone 2 architecture. And really what sets our architectures apart from competitive multicores is the internal switch fabrics, and this is what we call the multicore navigator and the Terranet. And really what those things are doing sort of behind the scenes when you're programming on the ARM and in a Linux world and you're offloading with OpenCL or OpenMP, these are all the things that are happening in the background to make sure that that code runs effectively on the DSPs and that you're really achieving the gigaflops per watt of the, close to the theoretical maximum. And without those, you can really suffer tremendously. So this is just an extension of our prior architecture. We're software compatible back to previous generations and expect that to continue forward. And again, as I mentioned, some of the key target areas here are radar processing, video analytics, and some focused scientific computing applications as well. One thing to point out is the Keystone architecture, we believe, brings a differentiation to the ARM performance. And if you look in the high-performance computing world, there's quite a bit of interest in looking at ARM-based systems and looking at purpose-built servers with ARM instead of Intel or x86 applications. And we think one of the things that sets us apart from almost every other multi-core ARM on the market and being looked at for high-performance computing is that we have greatly enhanced the bandwidth of the ARM cluster itself. So the bandwidth both internally and externally. So the access to external memory and the ability to move data around internally is at least 2 to 4x greater than any other multi-core ARM. So as well as being an A15 device and being on the latest ARM generation, by adding this enhanced memory controller, we believe people are going to see unparalleled ARM performance. And so in that, and it's really critical in the high-performance computing space, where you have large data sets and large amounts of memory being accessed. So the next slide will show sort of you can imagine a purpose-built server that only has these ARM plus DSP SoCs on it. And in this example, it could even be based on something like an ATCA rather than a traditional server architecture. And the reason I mention ATCA is because it has a lot of high-speed bandwidth for card-to-card connectivity running over rapid I/O, which is a protocol used often in communication systems and networks. And so I believe with our new devices here that we can see a change in traditional server development and the construction of these purpose-built servers, and even in different form factors than what we might have seen in the past, where almost everything is exclusive PCIe based. And the advantage of that is that we can enhance the bandwidth to to share data and memory across all the devices and all the boards much more efficiently than on a traditional PCIe-based way. So I think these work really well in a PCIe network, but I think it might work better in some other architectures. And I think we'll see some other architectures come to market pretty soon with some really sort of interesting and novel enhancements. And so if we look at HPC, we have advanced offloading architectures, and by that we mean with the ARMs offloading to DSPs. You can look at not only OpenCL and OpenMP, but TI has some other frameworks that are even more efficient that we could look at. And that could, if I make an analogy, there are some interesting architectures out there. I think in the Graph 500 space, you see some architectures and frameworks that achieve performance better than what you might get on traditional MPI-based ones. And so there are some things that we're doing in our software stack that would allow those frameworks to run really efficiently. We have 15 gigaflops per watt on our K2H12. Again, on the face of it, that might not, jump out. Given Supercompute 12, we're going to see all kinds of announcements about performance per watt. But when you really look at a system level and what's the entire power consumption of the server, not just the accelerator, what's the power consumption and cost of that purpose-built system, and how efficient is it at that job, I think you're going to see that we have a very competitive solution here. And then programming, as I mentioned, we do have OpenMP and OpenCL as well as some more interesting architectures. I guess could raise some eyebrows in some different areas. In general, we have a very strong multi-core development suite. We have our own co-composer studio for people that really want to get down to the detailed optimization. I know that in the HPC world, there are plenty of those researchers out there. So we have co-composer studio that allows access and debugging that's I would say unparalleled to other HPC type accelerators. Support C and C++, and now we have Linux, SMP Linux on the ARM cores, and we now have access to the entire ARM ecosystem and Linux ecosystem. So we think with this, we're starting to get to the point where HPC researchers and users can really jump on this technology and get to market quickly. So I think we spent a lot of time in the past year learning what the market requires, what people in the HPC space do with the devices, what's required for them to be successful, and we think that these types of ARM plus DSP SoCs will make it much easier for the adoption of these new HPC entrants like ourselves. So just to summarize, I talked mostly on the purpose-built server end on our new 668K 2H12 device, but there's a whole family of other devices. Some are really ARM only, and that's more for the traditional networking and Ethernet switching. And some are sort of cut downs or smaller devices that can go out to these endpoints, where if you look at a holistic view of the cloud and analytics and all the different things that are happening in that market today, where we can really make some revolutionary breakthroughs by providing the scalability from being not only the processor back at the server, but out at the endpoint. And so with that, I think I'll wrap up. We think we're really the first infrastructure or server class ARM plus accelerator device in the market. And for people looking to build some HPC systems and some novel architectures, we would love to talk to those people and see what we can do together over the next year.
Well, great. Well, thanks for that, Arnon. So a couple of points of clarifications, just so I got it here. Have you integrated the ARM chip and the DSP onto the same package?
Yes. So it's one package. It's one device. You have a cluster of 4 ARM cores. So you have a multi-core ARM cluster of 4 ARM cores, and you have a multi-core DSP cluster of 8 DSP cores. And they are very tightly interconnected through our memory controller. And so that's sort of the point about the general purpose compute system being tightly connected to the offload system. So in a heterogeneous compute network where maybe traditionally it's x86 and GPU over PCIe, we're much more tightly connected between the ARM cluster and the DSP cluster now.
And then, so when you bring the ARM piece to this puzzle, what does that bring to the table in terms of the DSP? What does that offer the end user?
So what we learned is that most users in HPC are Linux programmers, And while the DSP supports Linux, it doesn't have full support of Linux. And so by adding that ARM cluster, we now have full SMP Linux mainline support, and that opens up a wealth of applications from the open source community for HPC, gives us better access to MPI, MPitch, and all the other frameworks that people use in this community. And so we think it'll be much more efficient and sort of tie into that development that people are used to. So if somebody's interested in playing around with a purpose-built server on our devices, we should be able to get up and running very quickly.
And so as a vendor, TI makes chips. Are you supplying like these motherboards with this setup, or the complete server, or how's that work?
We're not providing complete server, but we are working with a number of people to provide boards. So much as we had PCIe cards with our DSP only devices, you'll see with Advantech and other of our third parties, and even some potential server vendors, you'll see some custom architectures coming out over the next few months.
Well, terrific. So we're going to be at SC12. Will you be demoing this technology?
We won't be demoing this. We're just sampling now, and we'll be demoing this probably in about 6 months. But we will be showing sort of all the progress that we've made since we announced the DSP for this market a year ago. We have 4 different demos going on in our booth. So I invite everyone to come out and see all the progress that we've made and get some early indications of where we'll be with our next generation next year.
Well, terrific, Arnon. I think you guys are in the right space. Everyone's talking about low power and how that is so important for the future of HPC. So we'll definitely come out and check that out and see you guys at SC12.
Well, thanks, Rich. Really appreciate the opportunity to come back to your show.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.